Okay, today we are going to be talking about vehicle design as part of our topic of discussion. Before jumping into that, I need to announce that I am actually jumping on a plane later today and headed to Georgia Tech for a couple of days. I won't be back until late Thursday, so I'm hoping that I can get one of the TAs to come in and cover the lecture on Thursday. Thursday's lecture is going to focus on top-down skeletal assembly modeling. If you understand the techniques that will be covered on Thursday and again on Tuesday of next week, you should be able to organize your team in such a way that you can divide and conquer on all of the modeling that goes into your RC race car. Instead of worrying about where the part goes or how the part gets assembled, that's all controlled and handled by the top-down skeletal design. So if we do a good job of setting that up, you can then very quickly go and model parts, and they will automatically kind of configure and come into place and be oriented correctly and be the correct size and things like that. So the focus on Thursday is going to be to kind of get you launched so that you can do the planning, you can do the discussion amongst your groups. Relating to kind of getting organized, the students at UBC are now back to school, they are organized, they should be sending us all of their Skype names and things like that. So if you've had a little bit of a struggle reaching out to your team members, just be aware that we don't all start classes the exact same time and things like that. And so be patient, but be persistent. See if you can't get in contact with your team members. See if you can't begin getting organized. Part of today's lecture is going to talk about organization as we kind of move forward. So this is a car that I have kind of fallen in love with. The reason that I kind of have fallen in love with this car and want someday to kind of have one in my garage is because my oldest son was the lead designer on the 2010 Mustangs. He worked with a number of other designers, but he was over them. And so the way design happens in the auto industry is the one that comes up with kind of the best styling, the best design is generally given the responsibility to be the lead. And he gets to decide where the lines and where the brakes and where the shoulders and where the greenhouse and all of those different aspects of the car, where they fall. And so he did it not only for the standard 2010 Mustang, but he did it for the GT version and also for the Cobra version. So I kind of consulted with my son and asked him to kind of help me understand how automotive vehicle design is actually done. He no longer works for Ford. He's actually with a startup company here in Provo now, doing fairly well, but for a number of years had a lot of fun designing cars. So according to my son, he said the first thing that happens is they go out and they do a marketing study, and the marketing study tries to determine, you know, what the world, what their customer base is really looking for. Once that market study comes back and is handed off to designers, they go through a bunch of sketching. And so they sketch dozens and dozens and dozens of different looks of the car. They also work on styling and sketching up the inside of the car. So all of this is done kind of with pencil or marker in hand. It may be done using a computer, but generally all of the first stuff is just kind of rough sketching that eventually gets transformed into a computer version. Someplace early on in this vehicle design process, they begin building clay models, scaled versions of what they think this next car should look like. And oftentimes the scaled version is split in half, kind of nose to tail, and it's pushed up against a mirror. It just reduces the amount of modeling, clay sculpting that has to go into it. This one is a full car that they're sculpting, and it's pretty tough to get the right side and the left side to be perfect, and that's why they tend to push it up against the mirror. But plenty of times, they will do a full car, and they'll do one version on the left side, and they'll do a slightly different version of the car on the right side. Now, once they get the clay kind of in place, they have this material called Dynoc. It's a plastic sheet, and they can basically pull that sheet over the clay and use a little heat gun, and it sucks right down, and it looks like paint. It looks like a real car. Okay? So all of this sketching and all of this kind of craft work is done early on in the design stage, trying to figure out what does this next car look like. At some point along the way, they start doing some CAD work. They start rendering surfaces. They start kind of building it full scale. They start saying it needs to be this long, this wide, its track stance, all of that is kind of figured out. Okay? As they begin building the CAD model of their car, they have to begin worrying about kind of the ergonomics. They have to worry about, you know, how does the person fit inside? Is this car going to be sold in the United States? Is it going to be sold in Asia? Is it going to be sold in Europe? And what are the different size of people that live in those countries? And so they do a very intense study trying to figure out exactly the size and shape that the car needs to be in. As they begin refining their CAD models, they begin taking virtual mannequins, not just sketched up mannequins, but they begin taking virtual mannequins and placing them in the car and begin asking the question, what can this mannequin reach? When the seat belt is on them, can they reach to turn on the DVD or the radio or anything else? Because they now have a CAD representation of this, they can go full scale on the clay. Ford, General Motors, Chrysler, all of them have very large milling machines that can easily mill a full-size car. And the examples on these slides are showing craftsmen doing some of the fine detail work after these things have been machined out in clay. You can also see in this left-hand image that some of the Dynoc has actually been placed on the car. So that is just the plastic material that's kind of been wrapped over the vehicle. This is one of those very large milling machines. And so they can either mill it in high-density foam or they can mill it in clay. The high-density foam doesn't allow a sculptor to get in there and kind of tweak the design. And so if you're doing high-density foam, you need to use large tools to kind of rough it out, and then very small tools to do the detail work on the actual car. So as we're moving down this process, we're getting more and more refined models. We can take either the clay representation of the full-size car and push it into a wind tunnel, and we can begin looking at the aerodynamic capability of this car. So that's why they'll do a full-size model. Or they can take the CAD representation And with the CAD representation, they can begin doing aero studies, looking at the drag, looking at any kind of lift or anything like that on the actual car. So a lot of this is still kind of in the preliminary stage. The model is not perfectly refined, but they're wanting to get a handle on what this car, shape is going to look like. As they are still in the preliminary stage, there is all kinds of additional computer analysis and studies that get run. In the upper left-hand corner, this is basically a handling exercise. They use Adam's vehicle, which is a dynamic simulation and motion program, to how well the car handles if it's going to be doing a lane change. It can go in there and say the suspension needs to be tightened up. We need larger springs, softer springs. They can basically kind of look at the design and handling of the vehicle from a virtual representation. We can begin taking components of the car and doing FEA analysis. That's the lower left image. They're doing an FEA analysis on basically the rims of this car. Upper right-hand image is they have a basic representation of a vehicle, and they have different crash scenarios. So in the upper right-hand corner, the upper left image is doing a front impact. The top middle is doing basically a pull crash. This is what I did when I was I got my driver's license at 16, and I think when I was 16 and 2 days old, I wrapped my folks' station wagon around a telephone pole a little bit forward of the door. So it wasn't quite that impact scenario, but my parents weren't happy of what I did. This is a rear impact. So there's all these different impact cases, and all of those load cases have been taken and put into the computer, and then the computer's been asked to minimize the shape, minimize the overall compartment area, and so study the load path, study where we need to have material and where we don't have material. And this is basically the lower right image is a topology optimization. So they're trying to get weight out of the car. Why do you want weight out of the car? Better fuel efficiency. Okay? So this is one of the studies that they would do during preliminary design. Okay? Another study is just the actual overall kind of FEA impact. This is a front impact analysis. Other examples, they were on the previous slide, but here's just some more examples of kind of impact tests. But these impact tests are really focused kind of at safety. When you move into the detailed design, you're well into the second year of the car design. Typically a car takes 24 months today. It used to take 48 months to do a full-up car design. Most auto manufacturers have been able to reduce it to 24 months. When you're into the second year of the design, everything is becoming very, very well described. Every component, every fastener, they understand what's going to be welded, what's going to be glued. They understand all of the different types of interfaces and attachments that are going to be used to bring this assembly together. And they have it very well defined inside of the CAD system. Okay. What they do from that point is then they begin to really drill down in very, very specific analyses, very long computational runs, to say what are the real numbers. If we're going to publish a safety rating